Okay, in this video we're going to explore the Van de Graaff generator. We'll look at some of the basic demonstrations that we looked at in class, and then also we're going to go over some of the questions from the Van de Graaff lab. Before we do that though, it's probably worthwhile to at least get a basic understanding of how the machine works. There's several important parts. One is the dome at the top, which is where the charge is going to accumulate. And then on the inside of the dome, which you can't see right now, there's a roller and a latex belt, a rubber belt, that goes over the top and then goes down to the bottom and is held under a little bit of tension, so it's stretched out just a little bit. At the bottom, the roller is made of a different material, and that's really where the action is occurring, because the roller at the bottom is made of felt. And because felt and latex rubber are quite a ways away from each other on the triboelectric scale, the triboelectric scale I should say, what's going to happen is they're going to start to exchange charge. And as they do, the charge is going to be drawn off. Some of the electrons are going to be drawn off, and they're going to be sent out through the ground wire of the machine. Essentially what's going to end up happening then is the belt that is on the upward side will be positively charged, because it will have ejected some electrons as it passed the felt on the bottom. When it arrives at the top, it goes over the roller, but as it passes over the roller, there's a metal comb. It's literally almost like little metal fingers that reach down, I would say about a half a centimeter away from the belt. So as the belt comes up over the top, the belt begins to draw electrons off of the metal comb because it's a good conductor. So it starts drawing charge from the entire dome and neutralizes the belt. So the belt that's on the downward side is actually neutral. The result of this is that you start to build up a lot of positive charge, I should say, on the metal comb. And since that metal comb is connected to the dome here by a wire, this is going to start to build up a huge positive charge. Now, one of the things that's really important to understand about the Van de Graaff is that you can actually feel the electric field. It's almost like it's a sixth sense that human beings have. We can feel strong electric fields, and I'll explain to you how we can feel the field. The question that you're going to be asked is, why does it have that effect on us? So the first thing to see is how it discharges. So I'm going to turn the machine on. First, let's zoom in just a little bit though, so you'll be able to see it a little bit more clearly. And we'll turn the lights down just a little bit so that the discharge will stand out a little bit more for you. I'm going to discharge it in two ways. So first of all, I'm going to use the discharge wand, which is connected by a wire. This is also connected to the ground wire for the system. So again, this will just discharge harmlessly into the power supply, and it'll go down into the earth where it will spread out. So you'll see right now it's not discharging, right? So this is really important to think about the distance. The distance to the object that it discharges is really important. So you can see now I'm about, I would say about 4 inches away, and I'm getting a pretty good discharge. I can even get it to discharge a little bit further away, maybe about almost 5 or 6 inches away. But we don't have to discharge it just with the discharge wand. I can also discharge it to myself. I'm only going to do this a few times because it's actually quite painful. So you can see the little lightning bolts. They really like to go into the knuckles. They like to go into sharp, pointed places. It's quite painful, in case you're wondering. So ultimately, this thing was able to discharge through the air. I mean, the charge had to jump from the device to me, or from me to the Van de Graaff. So just to show you another demonstration of the idea that electric charge can pass through things that are not good conductors if the conditions are right, and that is your job, is to figure out what are the conditions, what has to happen in order for you to be able to discharge through the air. Let's push this down just a little bit so we can see it more clearly. I'm going to turn the Van de Graaff back on, and you'll see that there's a metal strip that runs along here, and then there's little gaps. Some of the gaps are really close, like this guy's only about 2 millimeters, but other gaps right next to it, that gap's probably more like 5 or 6 millimeters. I'm going to discharge it with the wand because it's really painful to discharge it on myself. You can see a little bit of charge discharging. You might be able to see it, but once I bring this up, you'll see it very dramatically discharges. So air can conduct electricity. Insulators can conduct electricity. They just don't do it very easily. They need the right conditions in order to be able to discharge. Okay, we'll turn the lights back on so that you can see the next demonstration more clearly. But before we go on to the demonstration, let's just revisit the questions from the Van de Graaff lab. So question number 1 asked you, how can the air conduct electricity? What conditions are necessary for that to occur? And what starts the discharge, or what triggers the discharge? When will the discharge occur? Those are the things you want to think about. Obviously lightning is one of the most spectacular demonstrations of electrostatic discharge, but what you just saw was on a small scale. So even in the house, I can make this discharge occur, but I just have to create the right conditions. The second thing we're going to look at is we're going to revisit the pit ball. And even though this is actually in the electrostatics lab, we've already kind of done the pit ball, I'm going to ask you to revisit it again to explain why the pit ball behaves the way that it does. Just because I'm in kind of a tight area here, I'm going to shorten up the cable just a little bit. Just to remind you, what you saw in the electrostatics lab was that the pith ball, I didn't need to bring the pith ball in to touch the charged object. Actually, the pith ball would reach out to touch the charged object. Now this is a much larger pith ball than we used in class. I mean, this thing is way too heavy. You would almost never be able to see any reaction if we were to do this with the little plastic rods. But with the Van de Graaff, we can build up quite a large charge. And when we bring the pith ball in close, you'll see that the first reaction is, first it's attracted, and now that it's charged, I'm going to let it go. Now that it's charged, it will keep that charge for quite a while. So question number 2, you're being asked to describe the way the pith ball reacted. First, it was attracted. Once it touched, it got some of the charge. You can see it keeps bouncing off of me and discharging. And then once it gets its charge, it'll stay charged for quite a long time. So attraction and then repulsion. That's what you're explaining for question number 2. But I also want you to think about something else. You'll notice that the pith ball goes back once in a while. Every once in a while it'll go back and recharge itself. It slowly loses its charge over time, but the pith ball is able to hold on to the charge for a pretty good amount of time. So I can keep this guy close to the machine and he'll pick up charge and then he'll keep it for quite a long time. Let's take a look at what happens if we change the shape of the object. And I'm going to do 2 different things to show you that. So first of all, I'm going to use a piece of aluminum foil. Just a small strip of aluminum foil. You'll see the same reaction. It's attracted first, then it repels, but it does something very different. And that is that it immediately goes back and recharges. Now you notice that the pith ball was able to hold on to the charge for much longer. So this is question number 3. Why does the shape matter in terms of holding on to charge? Round objects are really good at holding on to charge. That's why the dome on the Van de Graaff is shaped the way it is. But things that have very sharp edges, like this piece of aluminum foil, they don't hold on to the charge very easily at all. Let me give you a second demonstration of that. So you saw what happened with the Van de Graaff, that we can get a pretty good discharge from about 4 or 5 inches away. And so what I'm going to do is I'm going to prevent the Van de Graaff from being able to pick up a charge. All I have is a piece of wire. It's coiled, so it'll be able to sit on top of this. So I'm just going to tape it on there so that it makes good contact. Now I'm going to turn the Van de Graaff back on. I'm going to turn the lights off for just a moment, and we'll see how the Van de Graaff behaves when I put that on there and when I take it off at the end. So now I'll turn the Van de Graaff up. And you'll notice that I'm holding the discharge wand at about the same distance I was holding it before. Nothing is occurring. I'm down to 1 inch. I'm at a ½ an inch. I'm at a little bit less than a millimeter, and now I finally start to see a little bit of discharge. I get back out of the way, I don't see anything. There's no discharge anymore. Let me turn the machine off for just a second. Let's discharge this guy. Okay, so I'm going to take that off now. So now it's returned back to its normal kind of rounded shape. I'm going to turn the machine on to the exact same speed. And you'll see that at, again, about 4 to 5 inches, I'm able to get that loud, really large discharge. And that is because it is now able to hold on to that charge much better. When I put that wire on it, I give a nice sharp point, and that allows the charge to leave very easily. Okay, so again, that third question is about the shape of objects. Why do round objects hold onto the charge better than objects that have sharp edges? So one of the things I alluded to in the beginning is that human beings, It's almost like we have a sixth sense. We're able to detect electric fields. That's like a really amazing thing. And it is because of the hair on our bodies, on our faces, everywhere. Even though you might not think about it, there is hair on your forehead, there's hair on your cheeks, there's hair on your nose. There are tiny little hairs on your nose. And so as a result, that is what is revealing the electric field for you, is that the hair on your arm, on your head will start to stand up. My hair is a little bit too short to be able to do this in class. We can try to get somebody to get up, put their hand on this object, allow charge to start to build up on them, and then the hair on their head will start to stand up. Now, because I don't have anybody who can do that with me right now, I'm going to use this little device. I'll zoom in on it so you can see it nice and clearly. It's just basically little strings. And in theory, really, this is even harder to make this stand up because these little strings are much heavier than human hair would be. I'm just putting a little bit of tape on it so it doesn't slide off in the middle of the demonstration. Okay, so this guy is attached. Let's zoom in on that just a little bit so you can see it more clearly. Okay, we'll leave the lights on for this one. So now we're going to start to look at question number 4. Why do people's hair stand up when they become charged? So one of the things you, I'm sure, noticed is that it was almost immediately. Immediately they began to repel each other. Before they were hanging down right next to each other, they didn't care, they didn't mind being right next to each other, shoulder to shoulder. And now that they become charged, everybody is nice and evenly spaced. Look how evenly spaced they are. They naturally are going to try to avoid each other. Not only do they avoid each other, but they avoid the machine also because everything in here has the same charge. Now, one thing I want you to look at is what happens when I bring my hand in really close to this object. You're going to see the little hairs start to reach over towards me. Something's happening to me that makes them want to come over towards me. Now, I can also use the discharge wand to discharge it, and you'll see a dramatic reaction. When I take away some of the charge, they relax a little bit. Okay, we can turn the machine off. And what you're going to see happen is they will slowly begin to lose their charge. Now, in this case, it's not so much that they're losing their charge because of their shape, although that is definitely playing a role in it. It is because of the moisture in the air. Moisture is really good at pulling charge off of objects and just letting the charge go. And so you're seeing that some of them are allowing it to be released to the air a little bit more easily. Slowly, 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 the charge is beginning to dissipate. So when I say that I can feel the electric field, I'm saying I literally can feel it on my face. From this distance at about 2 feet, I can feel it on my face. It's as though something is touching my face. And the reason for that is because the hairs on my face are starting to stand up. The hairs on my arm will start to stand up. When I put my arm in at this distance, all the hair on my arm here begins to stand up. It's actually attracted to it. In fact, we can do this demonstration this way. I'm not even going to charge the hair. I'm not even going to charge the hair. I'm going to hold on to it. I'm going to keep it close by, but I'm not in any way trying to do anything to put charge from this machine onto it. And you'll see that it still has a pretty dramatic reaction. So you can see those guys are now doing the opposite of what they were doing before. Now they're very attracted. Everybody wants to get close to this machine. So something has happened to them because when I pull the object away and I hold it here in front of the camera, they distangle. Nobody wants to get anywhere near each other. Nobody's affected by anything. When I bring it close, they are somehow attracted. They can tell that there's an electric field there. Something is happening to them to cause them to experience that electric field and begin to move with it. And that's essentially what you're feeling when you feel an electric field. Now, if your hair were ever to start doing that, if your hair were ever to start standing up like that, you are about to be struck by lightning. So you really want to do something to avoid that. And so that's something to think about in the lightning lab. You'll do a little bit of research and find out good ways that you can protect yourself from being electrocuted. Most people do survive being struck by lightning, but it's not a pleasant experience, and it's just kind of a roll of the dice. About 1 in 7 people do die when they get struck by lightning. So if you were to experience this and you were out in nature and you suddenly started to feel your hair standing up on your head, or even if you could feel it on your arms, you're about to be struck by lightning. There's a huge pool of charges that's starting to build up underneath you because of a cloud that's passing overhead, and you really want to know what is the right thing to do. So we'll talk about that when we talk about the lightning in class. One last demonstration that I want to show you. This one is maybe the one that is most difficult to understand. So if I would say this is going to take you to level 4. All the rest of them you could get up to level 3, but level 4, this is the one that's really going to make you think a little bit. I'm going to use two different cups. So the two different cups that I'm going to use are, first of all, I'm going to use a metal cup. So this is a metal cup, and then I'm going to use a styrofoam cup. So a conducting material and insulating material. Inside of the cup, I have just some small pieces of paper. So just little small pieces of paper. They're colored, so they'll maybe hopefully be a little bit easier to see against the background. I'm going to place this cup on the Van de Graaff. I'm just going to put a little piece of tape on it so that it doesn't fall off from the machine vibrating. Okay, so question number 5 is essentially this. Why do the little pieces of paper behave differently when they're inside of a metal cup compared to when they're inside of a styrofoam cup? So we're going to turn on the Van de Graaff generator. It's not exciting. Nothing is happening. The little pieces of paper are sitting in there. I know this thing is charged. I know it's charged because if I discharge it like this, I can see that it is building up a significant amount of charge. Now, one thing you'll notice about the metal cup is it has nice sharp edges at the top. So I'm not getting the same discharge that I used to get, but I'm still able to, I know that there is charge building up on this metal cup. But the paper don't even seem to notice it. So now all we're going to do is take those same pieces of paper, we're going to pour them into the styrofoam cup. I'm going to tilt the cup just a pinch towards the camera. So hopefully you'll be able to see it a little bit more clearly. Styrofoam cup, I taped to it because otherwise the styrofoam cup will fly away. When the styrofoam cup builds up the charge from the machine, the two will repel each other and the cup will go flying. So I don't want that to occur. But now when I turn on the machine, all the little pieces of paper go flying out. It's like a little confetti cannon. Notice it's building up a nice big charge now. So that cup is not allowing the charge to leave very easily, but for some reason, when the little pieces of paper are in a styrofoam cup, and the styrofoam cup begins to build up a large charge, little pieces of paper start to jump off, but in the metal cup, they don't jump out. So that is your final question. Let me just read that question for you. What you're being asked to do is to develop a model, a working model that explains why the paper stays in the metal cup, which is a conducting material, but flies out of the styrofoam cup, which is an insulating material. What is it about the two different materials that causes one of them to let the paper go flying? So that's your job. You can look up information in the book or from the notes, or you can look up anything on the internet if you would like to, but you want to develop some kind of model that explains why the paper is acting differently in one material than it is in the other. So those are all the Van de Graaff, the main Van de Graaff demonstrations. We'll do a few others in class also, but essentially this is what the Van de Graaff can do.